Hello, everybody. I'm Martine Cohen-Pelal, and I'm very happy to welcome you in this educational symposium. So the expert forum of today will be about microbiota and bone. I will be your chair, and I will be also accompanied by Nicolas Bonnet and Marie-Noëlle Orcajada from Switzerland. We have the pleasure to have two outstanding speakers today. The first one is Laura McKibbe from the United States. She will give a talk about the gut and bone signaling, is microbiota the immunological link. And the second talk will be given by Roberto Pacifici about the regulation of bone by microbiota from mice to humans. This session will be followed by 3 questions. So please use the Slido to answer the questions. And then we will move to the question and answer session for 30 minutes. So I'm very happy to first introduce Laura McCabe, who will talk about the gut and bone signaling. Thank you. Thank you for attending, and thank you, Laura, for the talk.
Okay, thank you. I'd like to thank the organizers for inviting me to speak at this session and talk about the microbiota and the immunological link of to the bone in the regulation of bone health. I have a few disclosures. And I'd like to begin by providing an outline of where we're going to go. First, I want to review the microbiota in the gut, update you a little bit on microbiota and bone, and then we'll focus on the role of the immune system in the gut-bone signaling, looking at the immune system in the intestine and the barrier, and then the immune system in the bone. And I'll end with a few slides on other signaling mechanisms because there are many mechanisms involved in this signaling pathway. So first, the microbiota. So the microbiota is a community of microorganisms living in or on the host. And it's composed of bacteria, virus, phage, fungi, archaea. Those are all in your GI tract, and they're microbes and they comprise the microbiota. And those microbes are influenced by the environment, which comes through your GI tract because it's this tube of the outside inside you. And the environmental cues include many things, including a high-fat diet, prebiotics, probiotics, medications that you take, chemicals, even lifestyle like exercise can influence the microbiota composition in your gut. So the microbiota is sensing the environment, and then it can affect the body through signaling. So what's actually happening in the gut? So we have the microbiota here. This is a healthy intestine, a nice balance of healthy bacteria versus non-healthy bacteria. And you have a mucus layer as well as antimicrobials that are secreted to help protect these epithelial cells here from any bacterial signals. And these antimicrobials are secreted by the Paneth cells. We also have another layer of protection, which is the tight junctions that really help to tighten that barrier between these epithelial cells so that nothing can leak through inside the body. And finally, we have an immense immune system that is in the GI tract. More than 70% of your immune cells are patrolling the GI tract, making sure that pathogens and bacteria aren't crossing over, or if they are, that they're being killed. So a healthy microbiota and a healthy barrier are very good things, but they can go out of balance. And so when you get an increase in unhealthy bacteria, you can see a decrease in the mucus layer. And you can also see increased apoptosis and decreased gap junctions of the epithelial cells, which ends up making holes in this barrier. And that allows for leaks. So you can have barrier leaks where the factors of the bacteria or the bacteria themselves cross over into the lamina propria. And as I noted before, that can lead to activation of the immune cells. And then those immune cells and their cytokines can enter the bloodstream. And the bacteria and their factors can enter the bloodstream and move systemically. And that can potentially affect the bone. So now I want to tell you a little bit about the link between the microbiota and bone. So we know that microbiota depletion or manipulation can affect bone. There are many studies looking at germ-free mice that have no microbiota, or germ-free mice where microbiota of a specific origin is, or composition is given back to them. And those are gnotobiotic mice. And those show that this manipulation of the microbiota can affect the bone density. Similarly, chronic antibiotic treatment where you reduce the microbiota also affects bone density, and acute antibiotic treatment where you can promote a dysbiosis can cause changes in bone. So that's direct manipulation of the microbiota. But there are other ways where we can find changes in microbiota. And that's when we look at the conditions that mediate osteoporosis. So I've listed the primary menopause, osteoporosis, and also secondary mediators. And of those, they all change the microbiota. There's studies suggesting this link between altered microbiota and these mediators. And I've circled a few here showing which ones are known to be associated with altered microbiota. And here's some other ones, not only from our lab, but other labs. And in this talk, I'm going to focus on these circled red ones, menopause or estrogen deficiency, colitis, excess glucocorticoids, and post-antibiotic dysbiosis. The other aspect, so we know now that conditions associated with osteoporosis are associated with dysbiosis. And so now we can think about how we can manipulate the microbiota to prevent the osteoporosis. And so probiotics and prebiotics are ways to do this, and they can have an impact on menopause, growth, aging. There's also sex-specific responses, and they can influence the bone loss in various conditions, and they do this beneficially. So to kind of sum up where we are right now, the gut, when there's a dysbiosis, can lead to inflammation and barrier leaks. That leads to signals to the bone, and that probiotics or prebiotics, these good factors that make the gut healthy, somehow prevent the signals, the negative signals, and they can also directly affect bone with their metabolites. Now, what exactly are these signals? So when we look at the microbiota signals, they go systemic, right? If they need to affect the body and the overall health, we need something systemic, and we might even have them going to bone. And there are numerous ones. I've listed some here. Some of these have been shown to influence bone. Of course, this gut barrier we'll talk about, the immune cells we'll talk about, but nutrient metabolism, so short-chain fatty acids, long-chain fatty acids, polyphenols, a regulation of TMA to TMAO, amino acids, synthesis of vitamins, and even the microbiota can signal through local production of incretins. We know incretins regulate osteoblast activity, serotonin, and liver signals. So first, because of this talk, we're going to focus on the immune cells, and I'm going to talk about the immune cells in the gut, and then the immune cells activity in the bone. So first, the gut. So the intestinal immune signaling is complex, and immune signaling in general is complex, but I'm going to give you a simplified version of this. So there are, of the bacteria, I've also included the segmental filamentous bacteria, which play an important role in bone responses too, but you have other commensals, and they all have what are called these microbiota-associated molecular patterns, MAMPs. So those are pieces on the bacteria that can influence signaling. There's also PAMPs. Those are pathogenic associated molecular patterns. And so these pieces of the bacteria on the membrane, for example, can signal through the epithelial cells and increase apoptosis if it's a negative signal, decrease gap junctions, and promote barrier leaks. And they can also signal through the toll-like receptors, which recognize these patterns, and those can lead to signals that move into the lamina propria. They also can have metabolites that signal through to the lamina propria. And in here, they can affect the immune cells, like macrophages, to secrete various cytokines. Some can be pro-inflammatory, which can influence the immune cells, like Th17 cells. And you can also have signaling where there's an increase in IL-10, which we know is good for the gut and barrier function. And that can affect Tregs, so promote T regulatory cells. And then those can influence other T cells locally and affect their ability to promote inflammation or not. So this gut-bone linkage has been seen actually years ago when people were studying the colitis, inflammation of the gut, and showing that it causes bone loss. So we can treat mice with a detergent, dextran sodium sulfate, and actually just chemically poke holes in the barrier. And what that does is increase inflammation in the colon, but it also increases inflammation in bone. So there's a link between an inflamed gut leads to an inflamed bone. And this shows that the colon TNF levels are associated negatively with bone volume fraction. So the more TNF you have in the colon, the less bone you have. And intestinal leaks just naturally occurring with disease conditions are linked to bone loss. So this shows the bone loss that we see with post-antibiotic dysbiosis. And this is fitzy-dextran, which is given orally and crosses the barrier into the blood. High levels of that says that there are leaks. And there's leaks in the dysbiotic mice, and there's lower bone volume. Similarly, the inflammation in the colon is linked to lower bone volume. And in the glucocorticoid model, where we chronically treat, there's less bone volume. And there's an increase in serum endotoxin that's linked with low bone volume in these mice. And to kind of link it to bone, the increase in serum endotoxin is positively associated with an increase in dying osteoblasts in the bone. And Roberto Pacifici's lab has shown similarly that this leak in estrogen deficient mice, which are in the red dots, they have more phytidextran in the blood, so more leak. And that leak is also seen in humans where there's estrogen deficiency, and we know that's associated with bone loss. And we can prevent barrier leaks with probiotics or other treatments that prevent bone loss. So we've shown Lactobacillus reuteri under various conditions, ovex mice, healthy mice, diabetic mice, dysbiotic mice, prevents bone loss by preventing barrier leaks. And Roberto's lab has shown in that menopausal model, the estrogen deficient mice, that LGG and VSL3 decrease barrier leaks and increase bone density. We've also shown that the requirement for the response to the probiotic depends on lymphocytes. So the positive effects of probiotics in mice when we treat with LR, the Lactobacillus reuteri, are lost in RAG knockout mice, which don't have mature B and T cells. And similarly, we can't get a response to Lactobacillus reuteri in female mice unless we induce some inflammation. And Fraser Collins went on to show that the Lactobacillus reuteri can directly produce factors that affect the lymphocytes and their cytokine expression. And finally, for the barrier, MDY, which enhances barrier function, shown here, decreases leaks, increases bone formation in a dysbiotic model, but also the glucocorticoid model, prevents leaks, increases bone density, and then we have the link to bone where it decreases osteocyte death. So now let's go to bone. So I'm going to focus on the osteoblasts and just note that T cells are critical in regulating osteoblasts through TNF, which downregulates bone formation, and Wnt10b, which upregulates bone formation. So Wnt10b is key to enhancing osteoblast lineage selection over adipocytes, and it prevents osteoblast death. And we've shown in our models, like the glucocorticoid model, that the treatments that prevent barrier leak prevent Wnt10b suppression. And this is also seen in diabetic mice that L-reuteri prevents Wnt10b expression and diabetic bone loss. And Roberto Pacifici has gone on to show that LGG stimulates Tregs to promote CD8 T cell production of Wnt10b in the bone, which stimulates bone formation. And finally, a nice paper that's come out from Roberto's lab shows that if he blocks lymphocyte migration from the intestinal lymph, he can prevent chronic PTH-induced bone loss. So again, you need these lymphocytes to benefit bone health, but you need the lymphocytes as well to cause bone loss. So the immune cells within the gut are intricately linked to the response in bone, whether it's positive or negative. And this just shows the suppression of the T cells activation in the bone marrow with the inhibitor, and then those mice actually didn't lose bone when they were treated with PTH. So there are other pathways to consider. I don't want to suggest that these are the only pathways. We know that probiotics specifically make a number of components. I've listed some here, and we can take those and add those to osteoblasts in culture and see a variety of effects. So some examples that we found is that the factors produced by L. reuteri can prevent TNF suppression of Wnt-B. They can also prevent osteoclastogenesis in vitro. And then there are other studies showing that other organs can be involved, so that Chad Novins has shown that a role for the liver in the gut signaling to bone, so gut, liver, bone. And there are other studies suggesting gut, brain, bone. And more recently now, a paper came out showing that the temperature, warmth can be added to the list of factors affecting the microbiota and bone, just adding to how dynamic this response is. So I want to quickly recap for you what's happening. So we have the gut and dysbiosis, which leads to inflammation and barrier leaks. We've shown that, provided data showing that these immune cells can go to the bone and release TNF alpha to suppress osteoblast function and Wnt-B levels and lead to bone loss. On the other hand, probiotics or prebiotics can produce factors that promote Wnt signaling in bone and promote those osteoblasts, those cuboidal wonderful cells building bone in bone, and prevent bone loss. So with that, I'd like to thank some of the key people, of the researchers in the gut-bone signaling area, which is booming, but also thank Fraser Collins, who was a postdoc in the lab, who worked a lot on the immune work, Nara Parmaswaran, who's my colleague and PI of the lab as well, co-PI, who works on the immune system, and of course, the grad students and everyone else in the lab. Thank you.
Ladies and gentlemen, the term human microbiota is used to refer to the totality of microbes that lives in close contact with our body, whereas the term microbiome refers to the genes produced by the microbiota. The gut microbiome is the largest, richest, and most complex microbiome of the human body. And perhaps the behavior of this child, which would be hated by almost every mother in the world, serves a very useful function in terms of generating diversity in the gut microbiome. It is now known that the microbiome regulates bone. In fact, the gut microbiome regulates postnatal skeletal development. We know that antibiotics alter bone mass. We know that probiotics increase bone density. And women with and without osteoporosis have a different microbiome composition. This observation raised the question of how does the gut communicate with bone? And perhaps this may be mediated by translocation of bacterial products such as LPS, trafficking of immune cells, absorption of bacterial metabolites such as butyrate, or maybe through increased production of IGF-1 by the liver or through vagal nerve signaling. Recently, it has become known that the gut microbiome is required for estrogen, parathyroid hormone, and glucocorticoid to regulate bone formation and bone resorption. These findings provide us with the opportunity to understand how the gut microbiome communicates with bone. And parathyroid hormone serves as a very good example of that. Parathyroid hormone is particularly interesting because of its multiple effect in bone. When PTH is injected daily, a regimen called intermittent PTH, high PTH treatment, PTH induces bone anabolism. However, when PTH is infused or produced continuously, as in the case of patients with hyperparathyroidism, the hormone causes bone loss. So the first question that I would like to address is whether the microbiota plays a role in the bone anabolic activity of intermittent PTH treatment. The rationale for this question is provided by earlier studies in which we show that intermittent PTH treatment increases bone formation by causing an expansion of bone marrow regulatory T cells, indicated as Tregs. These cells stimulate the expression of Wnt by bone marrow CD8 positive T cell. Wnt is a Wnt ligand that activates Wnt signaling in osteoblastic cells, stimulating bone formation. Since the microbiota is also known to cause an expansion of Tregs, we hypothesize that PTH may need the cooperation of the microbiota to expand Tregs. To test this hypothesis, mice were treated with daily injection of PTH for 4 weeks. At the same time, mice were also treated with wide-spectrum antibiotic to deplete the microbiome. This slide shows that antibiotics completely prevented the increase in bone volume and the increase in bone formation induced by PTH. Next, we conducted an experiment using germ-free mice. These animals are born and raised in sterile isolator like the one depicted here. Germ-free mice have no intestinal bacteria. Germ-free mice did not exhibit an increase in bone volume or bone formation in response to PTH, confirming that the microbiota is required for PTH to exert its bone anabolic activity. In the next few slides, I will present evidence that the microbiota is required for the activity of IPTH because it induces the production of butyrate, a short-chain fatty acid that easily diffuses in blood vessels and from there to bone. The left panel shows serum butyrate levels. As expected, antibiotic treatment decreased butyrate levels. When we fed mice with the amount of butyrate required to restore physiologic levels of circulating butyrate, under these conditions, PTH was able to increase bone volume. So this shows that butyrate supplementation was sufficient to overcome the negative effects of antibiotics and to reestablish the capacity of PTH to increase bone volume. Since it is well established that butyrate induces Treg differentiation, we reasoned that physiologic levels of butyrate may be required for PTH to expand Tregs. This was demonstrated by the finding that butyrate supplementation restored the capacity of IPTH to expand Tregs and to increase Wnt production in antibiotic-treated mice. Butyrate increased differentiation of Tregs through multiple mechanisms, including activation of GPR43 signaling. Studies conducted in global GPR43 knockout mice show that silencing of GPR43 blocks the capacity of IPTH to expand Tregs and the capacity of IPTH to increase the production of Wnt. Silencing of GPR43 also blocks the capacity of PTH to increase bone volume and increase bone formation. From this data, we concluded that the presence of the gut microbiota is required for PTH to work because the microbiota produces butyrate. This metabolites diffuses through the bone marrow, where through GPR43 signaling in dendritic cells allows and potentiates the capacity of PTH to induce an expansion of Tregs. These cells induce the production of Wnt by CD8 positive T cells, leading to the activation of Wnt signaling in bone and stimulation of bone formation. Several clinical trials have shown positive effects of probiotics in bone. We investigated the activity of one particular probiotic, Lactobacillus GG, and we found that this probiotic also increased the production of short-chain fatty acid, and in particular butyrate in the intestine. You can see here that LGG increased the level of butyrate in the intestine and the level of butyrate in serum. Now, butyrate, as mentioned before, is capable of expanding regulatory T cells. And interestingly, this activity can be blocked by treated mice with CD25 antibody. This slide shows that LGG expanded the number of bone marrow Tregs by the same amount by which butyrate does. However, treatment with CD25 antibody blocked the expansion of Tregs. So that provided a means to assess the importance of the expansion of Tregs in the activity of LGG. In this slide, we see that by in vivo micro-CT measurements, that LGG caused a marked increase in bone volume, which was completely blocked by treatment with anti-CD25 antibody. And this demonstrates that the anabolic activity of LGG requires the expansion of Tregs. From this and other study, we concluded that the probiotic LGG increases bone formation by enhancing the production of butyrate well above physiologic levels. And this high level of butyrate again expand Tregs and activate Wnt signaling production by CD8 T cells, leading to activation of Wnt and Wnt signaling and increased bone formation. The difference between the effect of treatment with probiotics, LGG, and treatment with PTH is that the probiotic increases butyrate levels well above physiologic level. And under this condition, there is no need for additional stimuli to increase Wnt. Whereas in the case of PTH, butyrate is only produced at physiologic level. And in this condition, co-stimulation by PTH is required to expand Tregs and activate Wnt production. The next question that I would like to address is whether the microbiome plays a role in the bone loss induced by primary hyperparathyroidism. This question was brought up by previous studies in which we showed that both in humans and in mice, PTH causes an expansion of Th17 cells, a highly inflammatory population of T cells, which produces IL-17, a very potent osteoclastogenic cytokine. IL-17 stimulates the production of rank ligand both by osteoblast and osteocyte, leading to bone loss. In this early study, we showed that PTH increased the number of Th17 cells in the bone marrow. But we now know that Th17 cells are mostly produced in the gut in response to the presence of specific saprophytic bacteria. So this led the question of whether the microbiome is required for PTH to work. To test this hypothesis, mice were treated with a continuous infusion of PTH, CPTH, for 2 weeks. Mice were also treated with antibiotics. The data showed that antibiotics completely blocked the bone loss and the increase in bone resorption induced by PTH. In another experiment, mice were treated with a low-calcium diet for 4 weeks. This treatment causes secondary hyperparathyroidism. And again, in this model, antibiotic treatment blocked the bone loss and the stimulation of bone resorption induced by low-calcium diet. In a third experiment, germ-free mice were fed a low-calcium diet in order to increase PTH. This experiment revealed that in germ-free mice, low-calcium diet does not induce bone loss and does not stimulate bone resorption. Now, we also found, as in our previous studies, that PTH treatment expands bone marrow Tregs, an effect that was blocked by antibiotics. But surprisingly, we also find an expansion of Th17 cells in the gut. This may suggest that intestinal Th17 cells migrate to the bone marrow, accounting for the expansion of Th17 cells induced by PTH. So the migration of Th17 cells is regulated by specific chemokine gradients. Circulating S1P is a ligand for the Th17 cell receptor S1PR1, and S1P attracts Th17 cells from the gut into the circulation. Once in the circulation, Th17 cells migrate to the bone marrow, attracted by CCL20. This is a ligand upregulated by PTH, which binds to the chemokine receptor CCR6, which is expressed on T cells. So the upregulation of CCL20 attracts Th17 cells in the bone marrow. These cells then release IL-17 and cause bone loss. This pathway was demonstrated using inhibitory of S1PR1 signaling. Specifically, we treated mice with FTY720, an agent that blocks this pathway and blocks the egress of Th17 cells from the intestine. The data show that FTY720 was able to block the expansion of bone marrow Th17 cells and the bone loss induced by PTH. So inhibition of the exit of Th17 cells from the gut blocks the expansion of bone marrow Th17 cells. In another experiment, mice were treated with CCL20 antibody in order to block the influx of Th17 cells into the bone marrow. This antibody was able to prevent the increase in bone marrow Th17 cells induced by PTH and was also able to block the bone loss induced by PTH. So from this data, we concluded that PTH, in concert with SFB and other bacteria present in the gut, is able to induce an expansion of Th17 cells in the intestine. Driven by S1PR1 and S1P, Th17 cells leave the gut and enter the circulation. From there, these cells are attracted to the bone marrow because PTH upregulates CCL20. Th17 cells release IL-17 in the bone marrow, causing bone loss. The final question I would like to address is whether the gut microbiome contributes to the bone loss induced by estrogen deficiency. In a study conducted a few years ago, we showed that germ-free mice do not lose bone in response to estrogen deficiency, which in this particular study was induced by treated mice with luprolide, a GnRH agonist. the mechanism was found to be related to gut permeability. Let me explain this concept. Under physiologic conditions, bacterial products and bacteria that live in the gut cannot penetrate into the intestinal wall because proteins of the germs and clothing families, proteins that work as a cement that seal the space between individual enterocytes, prevent the entrance of bacterial products and the activation of immune cells in the intestinal wall. Estrogen deficiency causes a dramatic downregulation in the level of germs and clothing, leading to an increased gut permeability, penetration of bacterial products, and activation of immune cells in the intestinal wall. In this study, we found that estrogen deficiency increased the level of IL-17, TNF, and rank ligand in the small intestine. We found a similar pattern in bone marrow. In fact, estrogen deficiency also increased the levels of IL-17, TNF, and rank ligand. And the simultaneous increase of cytokines in the gut and the intestine and the bone marrow suggests that the cells that make these cytokines may migrate from the gut to the bone marrow. We tested this hypothesis with a novel model, the Cayena mouse. These are mice that normally fluoresce in green. However, if their cells are exposed to UV light, the exposed cells turn to red. So in our experiment, we took Cayena mice, we subjected them to an ovariectomy. You see that the intestinal cells are all green. We exposed the intestine to UV light, so we turn intestinal cells red. And then after 24 or 48 hours, we counted the number of red T cells in the bone marrow by flow cytometry. Red cells can only come from the intestine and therefore provide a measure of the number of bone marrow cells of intestinal origin. We found that ovariectomy decreased the number of red Th17 cells in the intestine and increased the number of red Th17 cells in the bone marrow, demonstrating directly that Th17 cells migrate from the gut to the bone marrow. So in conclusion, we found that similar to what happened with PTH, estrogen deficiency causes an expansion of Th17 cells in the gut, their migration to the bloodstream, and then to the bone marrow. The difference between estrogen deficiency and PTH is that in the case of estrogen deficiency, the initial mechanism for this phenomenon is an increase in gut permeability that leads to the penetration of bacterial products. In the case of PTH, gut permeability is normal, but it's PTH in concert with bacterial products that causes an expansion of intestinal Th17 cells. And with this, I would like to conclude by acknowledging my collaborators, in particular Reinald Jones and Neil Weisman, and the postdocs in the lab that have done the work. And I would like to thank the NIH for supporting our work. Thank you for your attention.
Thank you. Thank you so much, both of you, for... Thank you. I think we are online again. Thank you so much, both of you, for this very, very nice talk. There is now so many informations about the new actors and also the new molecules, or the molecules that are already known with a new role. I would like now to ask you 3 questions that you will be able to answer. So please use the SciDo software using your mobile phone or another device. The first question is, how does the gut microbiome communicate with the bone? Via trafficking of T immune cells from the gut to bone, The second one via translocation of bacterial products like LPS, via absorption of bacterial metabolites, or all of the above. Please click the answers you think are the right ones and send your questions. You will have few seconds and we will see if most of you have followed and understood this very nice talks. I think this is it. So now maybe we will have the information. How many? Okay, so all of the above was the right answer, and it was the good answer for 86% of the people. So this is very good. So the next answer, the next question, please, will be the microbiota could be as possible target to improve bone growth, improve the acquisition of peak bone mass, or prevent bone loss, or synergize the anti-fracture treatment, or also ameliorate the bone mineral density through the regulation of adiposity. You may answer one or several questions. Please use the SciDo application to answer the questions. Hope that it will be as good as the previous one. Okay, so there is people voting. Okay, so it's moving. Please go ahead. So more than 64 votes so far. And I think we are almost stabilized. So the right answers were A, B, C, and D. And 95% answer prevent bone loss, 40% improve growth, and the others around 25% of them. So good answer too. So now we may move to the third question, please. Okay, so start to vote on the polling. Inflammation in the intestine correlates with increased serum osteocalcin, decreased serum endotoxin, increased Wnt10B expression in bone, decreased intestinal permeability leaks, and increased osteoblast death. Please vote using the polls for one or several questions, several items. So it's still working well. 32 people vote. Please go ahead. 39. Okay. A little bit more, I think we should be able to reach 60. Okay. So the answer was increased osteoblast death and you have been 46% of voting for this answer. So congratulations to all of you. So now, thank you for the good talks, and I will give the floor to my chairman and chairwoman, Nicola and Maria. Please.
Good morning or evening. Thanks a lot for these two excellent talks, and we got a lot of positive feedbacks, so thanks to our presenters. So maybe we're going to start by one question for Professor Maccabe. So actually, there is a kind of evidence at the preclinical level, not so much at the clinical level, and people were wondering how the link in between nutrition, microbiota and bone is today. Is it a strong or weak link, specifically in the dairy products, or also with polyphenols, for example? So do you have any comment on this?
Okay, so the question is about the role of the diet in the microbiota modulation and the importance in the milk products. So certainly the milk products have a lot of lactobacilli in them, which can be, as many of us have shown, researchers, many labs show that that can benefit bone health. And so milk products certainly are good. Fermented kefir or kefir, depending on how you say it, is a good thing. It has like 12 or 14 different kinds of probiotics. But interestingly, lactobacilli are also in kombucha, other like fermented products that you might not expect. So if you're lactose intolerant, there are other ways to get some of the beneficial probiotics. And then we know that prebiotics, so the fibers that we eat, so they're prebiotic because they support the life of the probiotics. And that's a really nice way to enhance the growth of the beneficial bacteria in the gut as well. And there have been some human studies, and of course, Connie Weaver has done some nice studies looking at the calcium uptake and using various prebiotics and showing this benefit. So there's definitely been studies that even translate to humans in that way.
Okay, we have also received a lot of questions for Roberto, and I'm going to pull a few of them. So can butyrate be used as a treatment with similar efficacy as a PTH? And there is also behind, what is the regulation of short-chain fatty acid at the circulating level? For example, can provide some information on the half-life of butyrate? You are on mute, Roberto.
Thank you for this very interesting question. There is a problem with butyrate, and the problem is that butyrate it tastes terrible and has a horrible smell, to the point that it's even difficult to convince mice to drink the water containing butyrate. So for this reason, many nutritional companies are developing fibers, butyrate fibers and other products rich in butyrate. They don't possess this negative connotation. There is a lot of interest for butyrate, as now is called a postbiotic treatment. So postbiotic because it's a product made by bacteria, and in particular by probiotic. For a number of clinical applications. There's a lot of interest in cardiovascular disease, there is interest in oncology, and indeed there is a potential in bone. So there's a lot of work translational work to be done in humans, but definitely there is the possibility of utilizing butyrate or other short-chain fatty acid as potential therapeutic for all conditions that can benefit from reduce systemic inflammation and an expansion of regulatory T cells, including bone diseases.
Okay, thanks.
So another question to Laura, actually. So the link between the gut-bone axis, so microbiota and so on, is more and more evident, let's say, in the literature, but what would be your opinion? Is it something that is more stronger in the bone loss or during aging, or in early life bone development? And what could be the key differences or modulator?
So I suspect that based on what's out there in the literature, that the gut-bone signaling is important for sure in growth. Julia Charles has done some really nice studies bringing in the role of the gut microbiota in IGF-1 regulation. And so there's definitely importance of the microbiota early in life. And then there have been studies that show that with aging, our microbiota changes and can become less diverse. So diversity, not only in the world, but also in our gut, is an important thing. And so we lose that as we age. And so that's, again, having the probiotics, fibers and things are very beneficial there. Are the signaling pathways the same? Probably not. So in the young, we're thinking growth and IGF-1. In old, we're thinking or aging, we were thinking of inflammation. And I think it's that inflammation that plays a role in the signaling process. And in that case, that's sort of different signals to suppress the inflammation or deal with that. So there are multiple mechanisms all around, but I think with all the different labs, they're contributing to that understanding.
Thanks a lot. So another question to Roberto, I think.
Yeah, people are asking, do we have some information regarding the role of microbiota on the link between diabetes and bone?
So that's a very interesting question, and there are a couple of postdocs in my lab that are anxious to address that.
Sure.
Laura in itself has done some interesting work in this area. So it is a rather complicated issue. So in the case of type 1 diabetes, there is certainly the inflammatory phase that leads to the destruction of the beta cells, where the microbiome plays a very important role. The bone disease of type 1 diabetes develops many, many years later. At this stage, the inflammatory phase that caused the insulitis is long gone. So I'm not sure that we can blame the microbiota for the bone loss of type 1 diabetes. But in type 2, it's much more likely that there is a direct link with the microbiota definitely contributing to loss of insulin sensitivity and the subsequent steps that lead to diabetes. We don't have evidence at the moment of a direct effect of the microbiome on the structural alteration of bone that occurs in type 2 diabetes. As you know, in type 2, bone density is normal or high, but there is a decrease in strength of bone. And at the moment, as far as I know, we don't have dramatic evidence that a structural change is regulated by the microbiome. But I like to defer to Laura, that knows much more than I do on this particular subject.
Well, I just know for the type 1 diabetes that we found that treatment with probiotic, Lactobacillus reuteri, benefited the bone health and prevented
bone loss in a mouse model. And we've also shown a role for Wnt. So the Wnt10B expression goes down in the diabetic bone, type 1, and it goes back up when we treat with a probiotic. So it might be, I mean, it's a good point, Roberto, that the early induction of the diabetes there's not the bone loss there, although we do see it in the mouse model, this slow loss that occurs early with the induction. But yeah, so definitely probiotics work there. We've done some studies with high fat induced insulin insensitivity, and
Laura,
we found
probably we have to close as soon as possible the discussion, which were really exciting, but we are out of time and we have so many questions. So unfortunately, we really like to thank you, the two speakers, for this really nice talk and a nice discussion. And actually, for the people who have asked so many questions, we will try to answer by chat. And with that, I think that we have to close the session. So I would like to again thanks everybody for this topic, which is really exciting. So thanks to you both.
Thank you.
Thanks.
Thank you.
Thank you.